Hi, Oleg.
Hey, can you hear me?
Yeah, we can hear you fine. And also with us, moderator of this talk, Sasha Varmin. Sasha, hi.
Hi everyone. Good morning, colleagues.
Good
Hey, good
morning. Good morning.
morning.
Okay, so we have some time to have a small talk. I want to say small talk. So, Oleg, could you share, in few words, what your talk will be about?
Actually, I have a few slides about that, but yeah, I can do a short intro for that even right now. So basically, today we will see RSocket, of course. This is my lovely topic, and we will see RSocket in action. We kind of I kind of prepared an upgraded application from another talk. I'll briefly talk about that during my presentation, but today we will be looking at real RSocket application in action. We will be looking at how good RSocket in solving different resilient problems, and by doing that, how it helps in improving microservices that we are building today. And yeah, this is basically the main topic. I will be showing different cool features. I would say that this is kind of advanced topic comparing to what I've been presenting before. I mean, it's not like an intro talk. It's just a hardcore. We will be coding. We will be running different microservices based on Spring and Spring Boot, and we will be looking at how resilient they are under the different circumstances. So this is basically the main idea of this talk. And yeah, I don't know what else to share with you.
Okay, go on.
Sasha. Sasha,
Okay, yeah, in this case, I'd like to ask a very simple and silly question. Oleg, in this case, why should I rewrite my existing application, which is based on an ordinary synchronous communication approach with RSocket?
So yeah, this is a good question. Why should we kind of refactor our application from the good all verified by time kind of imperative synchronous style to something else like reactive, for example, Webflux, or even reactive messaging with RSocket? So the answer is there is a couple of answers. First, you may not doing that at all, and you don't have to do if you are good with what you have. I mean, if you're running a small set of applications or services and you doesn't want to kind of scale to Netflix scale, then probably you don't need to care about like reactive, non-blocking, asynchronous at all, because this won't solve any of your problems. It will just give you more challenges. Of course, if I do that, I would use reactive as a first class citizen, of course, because I'm kind of easily understand how to do different things with reactive programming and functional. So for me, it's not a problem. But for other, functional and reactive may be a challenge, and to support like real enterprise application which doesn't scale much with this really hardcore functional and reactive can be just an overhead, which is unneeded. So the first answer, if you don't need to scale much, if you don't have much load, if you don't need to save your CPU and resources, then you are good. You don't need to do anything. On the other hand, if you're building high scalable, high performant applications, which must handle a lot of requests, which has to do a lot of I/O. I mean, I/O is like calling other services in order to get info, talking to databases, and you have like for example gateway scenario, or you have like other similar scenarios where you don't do any real computations and just kind of communicate as database with other services, then likely you might want to migrate to reactive programming. And you may want to migrate to Webflux first, because this is kind of the most familiar kind of set of technologies like HTTP and Project Reactor, which is already like 3 or 4 years on the market and available for everyone. So it's kind of easy task nowadays. But if you don't do again much I/O, then probably you don't need to do the flux. But if you want a really high performance, if you want to save, if you want to get like low latency, if you want to get like really high performance for communication between your services, if you want to make resilient system, because with HTTP it can be a little bit challenging to, as we will see in my presentation, it can be a little bit challenging to build resilient application and fast at the same time. I would say that that you may want to, if you want to get rid of these challenges related to HTTP, to slow HTTP 1.1, then you probably want to migrate to RSocket, because RSocket brings a lot of cool features related to resilience, related to performance, and as we will see during my talk, there is like a main feature which brings like performance, which is transport pluggability. I'm not talking about like multiplexing, because HTTP2 and like even upcoming HTTP3 are giving these capabilities and enable performance, but RSocket goes a little bit beyond that. It enables not just a single transport which is performant, it brings performance with flexibility, which is awesome. I really like this feature. And a part of that, it enables resilience, because with RSocket we went a little bit further than just a simple protocol. We created a protocol for applications to simplify the life of application developers of this like distributed and microservices applications. So yeah, it's a kind of, I went too far, but yeah, this is the answer.
I want to say that I really like Oleg for that, because you just ask him about RSocket and he starts speaking like for hours. I really love that. It's so awesome. That means that you're just in good words a fanatic of this technology. That's so awesome. I really love that.
Indeed.
So thank you very much for this answering before your talk, and it's time to start your talk. So let's do that. I see guys in YouTube waiting for that. So Oleg, good luck with your talk.
Thank you, and again, thank you for having me at this awesome conference, and thank you for organizing it. It's awesome that you're pushing community, and yeah, let's start. I'm just wondering, do we see my screen right now?
We will ask our operator. Yes, now we see your screen.
Okay, we should see console right now. I mean, some stuff in here.
Yes, it's here.
Okay, I just want to check that it's visible enough. That's the main question that I want to ask first. We need to see only the top one. The bottom one is just a minor things that I will be jungling with, and it's less important for users, like for our attendees. So
guys, please type something in YouTube chat. So if you can see like the console on the top, okay. So we have some delay with broadcast. Just a second.
Yeah. Okay. We will figure it out. But first of all, let me just start, and
yeah, sure.
Then you can interrupt me and say if I need to increase my phone or something like this. So welcome everyone, my dear friends, and I'm really happy to give this presentation about fast and resilient microservices with RSocket. So before we really start, because we had this small talk and I described like the main feature of reactive programming and of course RSocket, but you may be pretty new to RSocket topic, and you may be pretty new to microservices at all. I want to save your time before we start, because this is kind of an hour and a half long talk. That's why I want to save your time and say for whom this talk and what's going to be at this talk. Basically, this talk will be microservices. So if you're not kind of familiar or had kind of hands-on doing microservices, then probably this talk will be a little bit tough for you. If you are familiar, then we will be looking, of course, in RSocket in action. However, in order to get into RSocket in action, we have a couple of prerequisites. So first of all, in order to be on the same level, you need to know Spring and Spring Boot. Like, you have to have some experience, because everything that we will be doing is reading with Java and Spring. then you need to know reactive functional programming. Otherwise, it can be a little bit harder for you to grasp what's going on, because RSocket is about like reactive programming, is about reactive streams, and if you don't know this technologies, this ideas, it can be a little bit harder. But I'll do my best to explain it, so don't worry about that much. And finally, you have to have experience, as I said, with microservices and distributed system, because this is our main topic. So if you're good with what I say, then let me introduce myself. My name is Oleh. I'm software engineer. I've worked for Tanzu. Basically, I'm part of Project Reactor. Yeah, I recently joined this team after just 3 years in a row contributing to Project Reactor, and now I am part of this awesome team. So I'm really enjoying it. Just wanted to share with you. And a part of that, I'm driving and leading our socket project. And yeah, basically, I mean, this is just like an org role, but a part of that, the main focus for me, a part of like leading community is building our socket Java. And that's why we will be seeing during the whole talk everything with our socket Java and Spring. And if you're interested to learn more about reactive programming, back in the time I wrote a book about reactive programming with Spring 5, but this one is not about RSocket. That one is about like Webflux, Project Reactor, reactive concept, etc., etc. So let me start. As I say, today we will be talking about RSocket, but you may wonder, for those who have never heard about RSocket before, or have briefly heard about RSocket, let me just do a quick recap on what RSocket is. Basically, RSocket is a network protocol. It's absolutely open source. It's developed by community, and there is no company behind it. That's awesome thing. It's layer 5, 6 communication protocol, network protocol. Why it's important? Because if you remember, TCP, WebSocket, UDP is layer 4 in OSI model, and this one is layer 5, which means it brings session, it's bring application usability, it's bring some cool features like routing and so forth and so on. And that's why this application is more friendly for users, like HTTP, for example. So it's on the same level, I would say. And yes, we will see later that that type of layering brings a lot of flexibility for our protocol. A part of that, the main idea of RSocket is resilience, and the first-class citizen that RSocket brings to the user is Reactive Streams semantic. So again, for those who have never heard about Reactive Streams is a protocol, kind of is a specification on doing kind of streaming within a GVM, for example, or basically within a system. And now, like this Reactive Streams specification is implemented as a network protocol, so the same semantic, the same kind of messaging, the same on next, on error, on complete, and the same kind of main features like backpressure is ported as a network protocol and transparently goes through the network boundaries, so you can connect like you can, for example, if you talk about Project Reactor, you can start your flux on one service and you can subscribe to your flux on the other service, and they will be transparently talking to each other, and your subscriber will be transparently propagating its demand without any changes. So it's called application level kind of application level flow control, real application level flow control. I'm emphasizing on that because like in protocols like HTTP, there is transport level backpressure, which is not always good for all the scenarios, as history shown, for example. And a part of that, we have advanced resilience. So RSocket kind of inventors, basically, let me say a good word about the initial inventors and creator of this protocol, who are Ben Christensen and basically the Edge Network team, which was at Netflix, and who was working on this kind of protocol initially at Netflix in order to satisfy their needs. So they went a little bit further than just backpressure within the stream, since stream is a good, but sometimes we need like send in request response and request, for example, I don't know, fire and forget. And sometimes we need to control not just back pressure within a single logical stream, but sometimes we need to control back pressure within a whole connection in terms of number of requests, concurrency. So this feature is already in RSocket, and it allows you to build basically really resilient microservice. I will be talking about that a little bit later, but just did a little bit of introduction for that. And the most important, what make RSocket fast, is that RSocket is following the best practices shown by HTTP shown by HTTP3, and it enables those kind of practices and features. So RSocket is multiplex protocol. That's why it's 10x faster than HTTP 1.1. We implemented RSocket in different languages with a sort of performance and with a sort of small resource consumption. So this implementation can even be run on your IoT device with no problem. Actually, I'll just do this like separate. Like I'll move from the main story. Actually, currently I'm experimenting on kind of flushing RSocket CPP into just pure raw controller, and I'm almost there. So just follow me on Twitter if you want to get more updates. I will be sharing on my progress there. But yeah, we can deploy RSocket CPP, and you will get RSocket CPP on small tiny controller where you have just 4 MB of memory. It will work. Believe me. Alright, so this was a short intro. The last word that I wanted to say is that RSocket is basically developed in collaboration of great big companies who know how to build cloud services, distributed systems, and microservices, and that's why this protocol is really for microservices and distributed system, because all these people who had all these challenges related to microservices with a previous set of technologies understood what they need, and they build their needs in this protocol. All right, with that, let's move on. This was a little bit long intro, but let's have a look at our microservices scenario. So first of all, this talk basically was derived from one of my previous talk and my colleagues' previous talks. Basically, I have to give some credits to Yevgeny Borisov and Kirill Tolkachev, who initially initiated this first version of this talk. And I'll be giving some more ideas later about what was in that talk. But this talk is basically derived, and this example is derived from their talk. So what do we have? We have a microservices system, but this microservices system is basically kind of depicted or represented as a funny character from Soviet Union, well-known kind of series of like, yeah, it's not an anime, but it's like films, old films, whatever. So we have Pechkin. Pechkin is basically the first service. This is gonna be our client, and the main role of service of Pechkin service is basically to deliver different parcels. So Pechkin has parcels, and of course every parcel has a sender. But apart of sender, every parcel has a recipient. So our recipient for this story is going to be, let's say, Sharik. Sharik is basically a dog. This dog is just again from this Soviet Union film, series of films. And there is a sender who called Papa. Papa is basically from Russian, is a fuzzer. So Papa is sending a parcel to Sharik because Sharik requested some stuff. And this stuff is basically a shooting kind of shooting gun, like not like a shooting gun, but just for picture. So Sharik can chase different animals and can shoot them without killing them. So this is good. However, what if our Papa is a little bit suspicious, for example, and instead of sending just shooting, instead of sending a photo camera, he is sending, for example, a real shooting gun. So in order to prevent kind of a shot in the Prostokvashino, we need to do something. Yeah, Prostokvashino is a village where everything is happening within this small film. So we have this reactor, and we need to prevent this kind of malicious or unwanted sending of something wrong, like this shooting gun. And for that purpose, we have Pechkin, of course, because Pechkin is not that simple person. Pechkin is working for governance. So Pechkin knows to whom he has to go. And since like security departments are really care about security and like preventing unwanted situations, Pechkin sends all his parcels to kind of a couple of departments. The first department is basically encryption and decryption department. This department is responsible for carefully taking off the content of the parcel, and then since this is the main idea of this service of this department, he deliver the kind of investigation of the content into another services which is Big Brother. So we have Big Brother and we have Agent Smith on the right. And Agent Smith, after receiving the decrypted message or kind of unpacked parcel, he starts his investigation in order to understand whether this parcel has or has not some suspicious things in it. So this is our microservices, and our delivery man Pechkin will be sending messages and parcels to Big Brother. Big Brother will be doing some job and will be delivering the result of his job to Agent Smith. All right. So it sounds like, okay, how it's related to microservices. Actually, it's related. If we try to match this kind of set of services to, for example, some real set of services like API gateway, we will see that the matches is pretty similar, since we have some clients which are talking to API gateway. API gateway has a part of just doing routing. Sometimes it has to authenticate user, it has to do different validation. Like in Seer, we can implement anything in API gateway, and then API gateway deliver the particular request after some business logic done on this request to a particular destination or a set of destinations. So basically, this story is from real life, and we will be kind of looking into real world example. All right, coming back to our kind of Prostokvashino and Big Brother and Agent Smith set of services. So as I mentioned, Почтальон Pechkin or deliveryman Pechkin is sending messages to Big Brother. Big Brother decoding these messages and sending them to Agent Smith. And as we can understand, the speed of every service in this chain is absolutely different, because for example, collecting different parcels is not a hard job. Почтальон Pechkin and deliveryman Pechkin can just take the parcel from the sender and put it somewhere. We don't know where, but let's say it's somewhere. It's put somewhere, and then he takes all these parcels and immediately goes to Big Brother. However, Big Brother is pretty slow because he needs to carefully decode every message, extract the content. That's why it takes a little bit more time to do this work. And of course, department is not elastic. It's not like super flexible. That's why it has some limitations. And of course, Agent Smith is really slow because Agent Smith is carefully looking into every piece, into every object in this parcel, into every letter, in order to understand that there is nothing malicious in the content of this parcel. That's why we have really fast deliveryman Pechkin. We have somewhat fast but way slower Big Brother, and we have like really slow Agent Smith. So this is our setup, and with that, let's have a look at our application in terms of code. Folks, if you have any questions, don't hesitate to drop them into the chat. And yeah, let me first check that everything is good here. Okay, everything is good here. So let's move on. Here is our application. As I mentioned, this is just normal Spring application, and in this Spring application we have a couple of services. So we have AgentSmith, we have Big Brother, of course, we have PageCan service. But as you noticed, a part of these services, there are some other services, for example, like console dashboard, like metric starter, like something common, speed controller starter. So all this stuff that you are seeing is for support of this basically demonstration. The main services with which we will be working is AgentSmith, Big Brother, and PageCan service, of course. But in order to see what's going on these services, and in order to emulate within my local computer, like this small tiny machine, in order to emulate like real scenarios, we have like a console dashboard to collect metrics, and we have some additional things like metric collector for specific pools, and we have some common things and starters in order to simplify configurations and modifications of our services, because all of them are using pretty standard and common things. So with that, let me start a short intro into the services first. So these services are based on Spring Web Flux. So let me first open my configuration here and show you that here we have Web Flux, not here. Yeah, probably not here, but for example in this service, not in this, but yeah, probably in common. Okay. Yeah, here we go. Here we have Spring Boot Starter Web Flux, which explicitly say that right now all the services are using HTTP technologies. They're using Spring Web Flux, which is kind of performant and using Reactor for non-blocking and asynchronous messaging, and it should be good. We think that it should be good. And then every service is basically extending this common module and provide some set of things. So we have normal controllers here, like for example feedback controllers. This is less important. It's just like PageCan provided a parcel. The parcel went through to Big Brother. Then Big Brother sent it to AgentSmith. But since the parcel has to be delivered to a real recipient, we have to get back this parcel. That's why once AgentSmith is done with his investigation, he notify us that kind of the parcel is good, and we can take it off and kind of deliver to a recipient. So that's why we have like this feedback controller. But as you may see, this is just normal, well-known, kind of familiar to everyone configurations of our web API. So nothing new here. And a part of that, a little bit about PageCan. PageCan has later producers. So this is implemented basically for fake reason in order to emulate the real load. And as we may see here, basically PageCan is generating his data kind of without any stops. So whenever Flux got kind of requests that some number of messages has to be delivered, this generate function is triggered, and it will generate exactly this number of messages that was initially requested. That's why we basically use Flux here, and we want to see that basically this generate function is not overproducing messages and not kind of overwhelming the recipient with those messages, because if we got just unbounded requests, we will be just throwing messages without any stops, and probably the recipient will die. Yeah, let's move on. Then we have later distributor. So later distributor is basically the logic of sending messages to a particular service. It uses some pooling mechanism because in real world scenario, every service has resources, has its capacity, has its limitation basically, and these limitations are exposed in for example in memory size, in number of open ports, in number of like queued messages, etc., etc. So in order to emulate similar environment as we have in real world, we use a pool. This one is basically from Project Reactor. I use this pool from Project Reactor because it's non-blocking. It doesn't involve any threads. It's just using asynchronous and non-blocking Project Reactor, and at the same time it allows me to track what's going on within this pool. How many, for example, workers are required? How many workers are available? How many tasks are queued into the queue, and all these properties I can send to my dashboard that I'll show you a little bit later. So this is basically the producer setup, which is sending messages over the network. I'm using web client. This is pretty common and standard thing for Webflux. It's basically HTTP client with Fluent API, which allows me to say, okay, I want to send post HTTP request on this specific URI, and I want to provide this body, and I want to kind of execute start this request and convert like the response from the remote service to void, and yeah, that's it. I have here respond handler function. I'll be talking about this function a little bit later once I introduce the other configurations that I have in the service. So yeah, to be fast, a part of Pitchkin we have the other services, and the other services basically doing the same. They have similar configurations, similar controllers. So Pitchkin is sending messages to Big Brother. Big Brother is handling them, processing them. Big Brother using the same pool with the same kind of with the same setup basically, but with different configurations. And then once he transformed his messages, he sends decoded later to basically to the agent Smith in order to check it for suspicious and malicious things in it. And at the same time, agent Smith is identical, absolutely similar to the previous. Agent Smith is handling those messages using the same set of things, decoding like and analyzing the message, and basically send a notification afterwards to Pitchkin to say, okay, the parcel is ready to delivery, or we need to catch, for example, the hacker or someone else who wanna do an attack or send some suspicious and malicious things. So this is our basically services, and I've shown all of this just in order to give you idea that there is nothing complex in this application. This is pretty standard app. With that, let me move to basically to service common, not to service common, but to my adjustment properties.
Oleg, we have a small question in the chat.
Yeah.
So if you don't mind, I will interrupt you with this question. Why not just reuse the application's default pool to schedule async requests?
Sync request.
Async.
Because in order to schedule a sync request. So the question is, why not to use thread pools? If I understood it correctly, in order to schedule this request, basically. I wanted to build everything with reactive programming. If you wanna like in real world scenario, you would probably use the pool. The point here that the pool can be easily integrated with Project Reactor. You can do publish on, etc., etc. However, like in this particular scenario, pool doesn't give all the configurations that I need. I would be required, in order to use thread pool, I would be required to build like a lot of infrastructure around it in order to track the number of enqueued messages. Also would be required to kind of provide an asynchronous reactive wrapper, because everything that I do in my services is fully reactive. That's why, like, for example, notify a service. Everything is not here, but yeah, let's move to Pitchkin. Yeah, service, later distributor. So everything is fully reactive. We have just a stream, and it would be a little bit more challenging to configure thread pool in order to do the same. And for example, to reject properly exceptions, and I would require I had to build more code in order to do the same thing. That's why I basically use this reactor pool, but you are not required to use this reactor pool in your real application, since in your real application you have integration with real metrics. You know, for example, how many threads are allocated right now, how many threads are busy, how many kind of requests are enqueued into the queue of Netty or Tomcat. And basically the same thing can be done easier. All this demo environment is done for demo only, and in order to minimize and kind of make the size of everything, like the whole infrastructure, a little bit smaller, because I don't imagine how many requests I would have to send in order to crash, for example, Tomcat. But with this setup, I have predictable number of requests that I can send, and I know that, for example, if one extra request will go into queue, it will immediately kind of bounce it back with an error. That's why I can control this environment. I don't have to mess with all this servers and other stuff configurations, and it make my life simpler for demonstrating kind of real world scenarios. That's why I use this reactor pool.
Okay.
No other reasons.
Thank you for the answer. I just don't want to interrupt you in not a good moment. So if it will be time for questions, just call us and we will be here.
Sure. All right. Let's move on. I have shown all the services, and let's move to our service control starter in order to look at what other we have in our services. So I'm showing these configurations for basically providing showing you what configurations we have in our app. So we have a different set of configurations. We have a sender properties. Sender properties basically configure the error strategy, because you may imagine that at some point, if for example your real service is not responding to your request or starts erroring to your request, you wanna apply some error strategy. And for example, the simplest strategies that you can do is just fail. But over kind of this presentation, we will explore what other properties, error strategies we have on our client side in order to handle or do something with this kind of debouncing of our messages. A part of that, we have processing properties, and processing properties basically represents the capacity of our particular service. And as every system, it has queue size, it has some overflow strategy. For example, for scenarios when the queue is absolutely full, totally full, and you need to do something with the messages. And in a real world scenario, of course, we have much more complex kind of strategies, like dumping messages onto disk, or kind of offloading them to Kafka, or doing something else. But in general, the simple system has queue and has a strategy which can be terminate. For example, most of you seen this memory overflow, not Stack Overflow, but basically out of memory exception, which says, okay, you don't have enough memory to operate. And after this exception, likely your application gonna crash because it's really hard to recover from such an exception. Or for example, your application can be configured in order to error and debounce messages back, which is kind of real scenario, but imagine that your real microservices is overwhelmed, and if it's overwhelmed, most likely it's going to terminate for forever, and you would need to restart it. And for just demo scenario, we have blocking behaviors. Like if there is no capacity in queue, this queue will be behaving as a blocking queue. So once you will try to offer a new message, you will be basically blocked, and you will be waiting until there is a capacity in the queue. Of course, this is also possible scenario, but less likely, because our services just accept network calls, and they have nothing to do with saying wait, I don't want to accept your call, don't send it to me. It's less possible scenario in the HTTP world, for example. But for demo we have it. And of course, we have some other configurations like concurrency, because we can have multiple workers which processing task. We have time processing, the processing time or time of doing the business logic. And of course, every microservices has this kind of uncertainty. We never know how long particular request will last. We can kind of estimate. We can say, okay, it's gonna last for half a second or a second, but who knows what's gonna happen over the network. That's why we have this random delay in order to simulate different delays which might happen over the life of the microservices, basically. So this is a set of configurations that we will be working with, and every service has these configurations kind of mirrored in their configuration. So Pitchkin basically has 0 processing time. Whenever he is told that there is a parcel, he takes this parcel and kind of provide it to delivery service. Whenever he get a message, there is no random delay, so Pitchkin is pretty fast. We don't care about Pitchkin in this scenario. Pitchkin has a limitation in 100 of messages, so he can take at once 100 of messages and try to deliver them, or in queue at his kind of postman table. And we have only a single Pitchkin because he's pretty fast. He does his job pretty good. That's why the delivery service is not hiring other delivery or postmen. And for now, for start, it has blocking strategy, but it doesn't matter. And as a sender, he has this error strategy fail, which means that if for some reason the security department is not available, he would need to do something. And if such situation has happened, then most likely it's gonna fail and say, okay, I didn't deliver my parcels, and the delivery service will fire him most likely. But yeah, let's say that we have this fail strategy. The big browser has similar configurations. The big browser does fail. On the other hand, once the big browser is overwhelmed, he would say to Pitchkin, wait a little bit for me, and Pitchkin will be staying and waiting at the entrance until he gonna say he will be said that, yeah, you can come in, like in Soviet Union, like real world scenario, for example. And the Department of Agent Smith has 8 workers. He say, okay, my queue size is 100 of messages. That basically the number of messages which can fit into the department table, and the processing time is half a second for the demo purpose. And Agent Smith, as I said, is the basically the slowest one. It has only 2 workers. However, in order to process the message, it has to take 2 seconds, which is a lot compared to the other services. And the queue size is small because basically Agent Smith requires the Department of Agent Smith requires a lot of space in order to properly extract all the things inside the parcel and investigate on them. That's why the queue size is small, because no much parcels can fit into this department table. And again, for demo purpose, we have block strategy and retry strategy, because basically agent Smith will try to call multiple times to Pitchkin if he if Pitchkin is not available for some period of time. So this is basically our configuration. And just to start and see how it works, let me switch to the console. Everything that you've seen is deployed to remote service. Right now you are seeing a dashboard. In a second, this dashboard will get some more information about which we will be talking. So let me start. Let me stop Pitchkin. Let me switch to Agent Smith first. Yeah, because Agent Smith is. Okay.
Okay, Oleg, before we move forward, there is one more question in the chat. It is also related to the previous question about thread pool. Well, it is a question about web flags, that it already has a netty pool, and this netty pool and web flags should be abstract way for thread pool management. So what do you think? What's the better way of using thread pools, and why shouldn't we use existing thread pools?
I mean, you have to use existing thread pools. Yeah, that's the answer. As I mentioned, this application is for demo purpose, and I'm using things just to simplify the emulation of real world scenarios. In your real application, you have to use what is built into netty, into JVM, and that's it. That's fine. That's good. Nothing wrong with that. Again,
yeah.
My configuration's just for demo purpose, and nothing else has been taken from that.
Okay, great.
Yeah. On the other hand, you can learn, and you can probably know or don't know that there is Reactor Pool that you can use in your applications for some scenarios, which can be good. For example, Reactor Netty is using Reactor Pool for kind of doing connection pooling, and Reactor Pool is basically using inside Reactor Netty. So this is a technology which is used inside Reactor Netty, but for this scenario, my case is simplified, and I don't want to use kind of the configuration of Reactor Netty, and that's it.
Great, thank you very much for explanation. Okay,
Sure.
Go on, please, with your talk.
Yeah, thank you. So I'm starting the services. As we can see, I mean, it's enough for you to see that this is Spring Boot app, and it's enough for you that this app has Agent Smith name here, and it's running. And this one has Big Brother name. Yeah, and again, this is Spring Boot app. And this one is basically on the very left is Pitchkin, who is a delivery man. So this app is running, and now we see the dashboard, and now we can understand why all these metrics and what we have at this basically dashboard. First of all, we have services which are running at this moment. We have Pitchkin, Big Bro, Agent Smith. We can see the speed of message delivery for the services. We see the buffer size. For example, the red kind of color of buffers, or zero of 100, kind of means that the buffer is fully occupied with messages, so there is no free space. But as we can see, the service is up and running still. We can see the number of allocated workers. We can see the number of retries, because basically, as we will see further, retries is important characteristic of the service behavior, because if service retries too much, it means that something is wrong with this service. Of course, retry are kind of allowed, but we want to avoid retries, because this is just unneeded load, another service on another service, because we just say, hello, are you available? Hello, are you available? And so forth and so on. And the other characteristics that we see is the number of dropped messages, because I mean, dropped messages are not good, but sometimes they are acceptable. But yeah, we want to see what's going on with our services. That's why we have this characteristic here. All right, we see that the system works, and we see that the speed of Agent Smith is basically moving to 0.5. It's slowly kind of increasing its speed. So we will, after some period of time, we will see 0.5. Basically, this is the performance of two workers, which takes a job or a task and process it over 2 seconds. So if we do mass, we will see that the speed should be around like 1.5, like 0.5, sorry. And we can see that with blocking strategy, which is less realistic because none of the services will be waiting forever, our services are moving to the same speed of agent speed, which says that with blocking strategy, with synchronous message sending, we will have kind of backpressure. But again, this is just an illusion because in real world we do HTTP call, we open connection, and this connection reaches the endpoint and takes some resources. And even if you are waiting for the response, there are parallel threads which can ask more. There are other services which can also connect to this particular endpoint and ask for data. That's why in real world scenario you won't be seeing this kind of behavior. You will never wait for the response because everything is happening asynchronously, even if you code is synchronous. All right, so it says it works, but let's make this code more realistic. So what we want to achieve in at the end of our presentation is that all of our services are enabled with termination mode, which means that if our services fails or if our services get too many messages, it fails, because this is a real world scenario. If you get out of memory exception, you get out of memory exception and you fail. That's why we want to run our services in this mode, and we want to see that it works basically in this mode. Yep, stop. Okay. Come on, CD, base, and stop. Yeah, I killed the agent Smith. So we see that after I kill the process, the process is down. The same has to be done for this dude. Okay, Big Bro is down, and Pitchkin is down. So all the services are terminated. And now we want to run them in a slightly different mode. So as I said, we want to run every services in more realistic scenario where instead of blocking on overflow, we want to terminate the whole service. So we say, here I have a specific configurations. I say I provide a profile, which I'll show a little bit later. And this profile says terminate on overflow. So once my service is overflowed with messages, it will be immediately terminated. And I'm running this service with this configuration. Then I do the same for Big Bro. Instead of blocking, he has to terminate on overflow. And of course, if he got an exception back, he fails. He also fails with an exception, because if it's exception and if the message is really important, we have to turn down and do something with this message again, and or notify a user that he has to retry doing the same action, which is bad experience for user, of course. So we start this service as well, and we start our Pitchkin with this send fail, of course, and we will see what's gonna happen. So our services has started, and yay, a lot of exceptions. In a second, our Pitchkin delivered a lot of messages. Yeah, this number should be a little bit better, like bigger, if we got a little bit more time to send messages, but we've seen that the Pitchkin just started and delivered immediately 25 messages in a row. And of course, Big Brother doesn't have that much capacity to handle. That's why his buffer went over, and he immediately terminated. But before that, before the Big Brother terminated, our Agent Smith got too much messages because basically Agent Smith can take only 10 messages, and Big Brother is pretty fast, so he probably delivered more than 10 messages at once, and that's why Agent Smith fails first, then Big Brother failed, and then of course Pitchkin also failed with an exception, because he got no response or error response from the Agent Smith, which says that we need to apply some strategy in order to prevent our system to crash. So what can we do? This is a good question. As I said, there are a couple of other strategies that we can apply. For example, if the message cannot be delivered, there is no capacity in the buffer, we can drop a message, which can be acceptable. So let's see what's going to happen if we apply this strategy. So to emulate that our service is rejecting message, we will switch from terminate strategy to error strategy. So I have in my app, I have a set of profiles which I can easily use, and these profiles are like bring in basically different set of configurations which can simplify our basically investigation and play with these microservices. So we stop Big Brother and we run it with the same set of configurations, but instead of overflow terminate, we use overflow error, which means that if there is no capacity, we debone this message, we send it back with an error. And if we got an error, we will be dropping this message saying, okay, we wasn't able to deliver this message, we will be trying to send another message, and that's it. So we use send strategy drop, and here is this strategy. And for Pitchkin, we will be doing the same. So we stop in Pitchkin, and we, instead of fail strategy, we use strategy drop. And we start both services, and we will see what's going to happen. All right. So we see Agent Smith is up, Pitchkin is up, and all of them are up. We see that everything is fine so far. The speed of Pitchkin is pretty good. Pretty fast Pitchkin, but the kind of productivity of Pitchkin is pretty low because all of the messages are basically dropped, which is bad. And Big Brother is not that efficient as well because he probably throws half of the messages into the throw bucket. So we see that like most than a half messages are dropped. And Agent Smith is slowly working, just taking this number of messages that he can take, and the other are basically rejected. So the system is kind of work. Pitchkin is pretty fast, as I said. Like we will see 1,000 of messages per second, probably at like over time. But Pitchkin is absolutely inefficient, absolutely unproductive because all of these messages are dropped, which is not good. So what else can we do about that? So imagine that dropping messages sometimes work if you send in logs, for example, to some server. So dropping some number of logs can be acceptable. Or for example, if you're sending metrics to a metric service, if you have dropped part of the messages or part of metrics kind of status, nothing will happen bad. I mean, everything will be fine because the next message that will be accepted will show the real state of metrics. It's like not a part, it's a snapshot. It shows the whole state of the service which sends these metrics. So sometimes it's acceptable to drop messages, but sometimes if you send real user messages like a payment, it's absolutely unacceptable to drop and lose this message. That's why we need to apply another strategy. So what can we do? Probably if we got an exception, we can retry. Good idea. So let's do that. Let me terminate my Pitchkin service, Agent Smith service, and yeah, Pitchkin service as well, and Big Brother service. So all of the services are down, and now we wanna start Agent Smith with the same setup, because on the Agent Smith side nothing has to be changed. But on the Big Brother side, we have to, instead of dropping messages, we have to apply another strategy, which is retry. So instead of dropping messages, we need to continuously retry until we deliver these messages. And the other messages will be waiting in the queue until this particular message will be delivered. So this is a strategy that we want to apply. And finally, Pitchkin has to do the same. Instead of dropping messages, he has to retry. So he has to say, okay, big browser, are you available now? Are you available now? Okay, you're not. Okay, I will wait. He will wait. Are you available now? Okay, no, I will wait. And so forth and so on until all the messages which he carries in his hand will be put on the big browser table for processing. And then after that he gonna go to his table and take more messages for delivery. That's how our system will gonna work right now. And yeah, let's start and see if it works like that. So the Pitchkin is starting, and we can see that we got a burst of messages at the very beginning. So Pitchkin tried to deliver all of the messages that he has on his table in his buffer right away. However, after some period of time, he stopped because he's seen that the big browser is busy. So he started like checking whether big browser is available, disturbing big browser, spending Pitchkin CPU because Pitchkin has to stay and wait for big browser availability, and big browser at the same time has to all the time kind of move his attention to Pitchkin in order to say, no, I'm busy, wait a sec, and so forth and so on. So retries basically in the real world, they are not good as well because the service CPU is spent for something less useful, unuseful, let's say. The big browser, instead of recovering from and focusing on his business logic, he spent his CPU and his kind of availability and attention on saying, no, I'm not available, and sending error back. And our real services are doing the same when they are not in the good state, in the busy state, and they are disturbed by the other request that has to be processed. So instead of processing and spending CPU time on handling and doing real business logic, they have to focus and kind of spend threads and CPU on answering back to this request that they are not available right now. And after all, because in real world application we have timeouts, because none of the messages can wait forever, none of the application can kind of live forever, and none of the users can say, okay, I will wait for an hour until my payment will be processed. That's why some of the messages started being dropped, which is again the same previous situation as before, which is again a failure of this trial, which means that both of the strategies can work, but under the real load, in the real microservice scenario, they will fail. So we need to apply another strategy which can basically improve things. So we tried drops. What else do we have? Maybe rate limit. Correct. So another strategy which is commonly used and widely used in the distributed system development, in the microservices system development, is rate limiting. Because as you might know, rate limiting is basically doing the following. It says, okay, you cannot more messages per second as this, which says, okay, if we know the system capacity, so let's say Pitchkin knows the capacity of big browser, he can say, okay, he can guess, okay, I know that big browser is commonly processing like 16 messages per second. His department is processing this number of messages, so I should wait this amount of time in order to not wait for in the queue, in order to not wait like behind the door of the big browser department. That's why Pitchkin can do math and can say, okay, I will be going to big browser with this kind of period of time, and will be delivering messages to his department with this period of time, which can be a good solution. Sounds good. So let's try. Let's try to, okay, I need to terminate all the services. And now I need to change the strategy. So Agent Smith works as before. He has nothing to do with this configuration, as I said. The big bro need to change his strategy a bit. So we assume we want to make a trial that basically rate limit is a good strategy. The strategy which can solve problems, because this is well-known strategy and widely used strategy in many scenarios. So let's say, okay, if rate limit is good strategy, let's on the send of message, we will fail if something go wrong, if rate limit is not working. So we will see that basically rate limit is not working, we will fail immediately. That's what we want to do, and that's why we want to make this trial. So we want to make sure that basically rate limit is good enough. And a part of this profile configurations, we want to add one extra configuration, which is basically send /rate rate limit, and we have a prefix in this specific profile which says, okay, instead of fail I have to use rate limit. This is the wrong configuration. I have to change this one. So instead of fail I have to use rate limit, and since Big Brother is delivering messages to agent Smith, we say, okay, we know the capacity of agent Smith. That's why we will be applying rate limit, which is kind of identical to agent Smith capacity. So we do that. We start our application with rate limit agent Smith. We see that this profile is applied to our service, and now our Pitchkin has to do the same. But now we have to guess, okay, if agent Smith, if Big Brother applied his strategy to agent Smith, probably Pitchkin has to know only about the capacity of Big Brother. Sounds good, sounds reasonable. So if Big Brother can take like 16 messages per second, then it's reasonable to use this information for Pitchkin in order to kind of adjust his speed of sending messages. Reasonable, let's try. So this is the first thing that you probably will do when you're gonna build your system with rate limiting. And I'm doing the same. So we apply rate limit and we say, okay, we apply the rate limit strategy for Big Brother. And we start a service. While it's starting, let's go back to logs and let's see what's happened. And something went wrong. For some reason, Pitchkin tried to deliver 6 messages per second, not much of the messages, but he failed. He failed with an exception that too many requests was sent, and this message was from Big Brother. And at the same time, Big Brother has also failed because probably he filled in his queue, but he got much more messages. Probably. So let's see what's happening on Big Brother side. On Big Brother side, we got an error dropped. Do not permit further calls. Okay, this is because our pool is terminated, but the reason for this message is, okay, there is no reason for this message. It's too long kind of stack trace, which is common to reactive application. But in order to understand what happened, let's have a look at our profile configurations. So we want to open basically rate limit agent Smith, and we see that we enable rate limiting, and we say, okay, the rate limit for agent Smith is 2 messages per 2 seconds. So basically it's going to be like 1 message per second. Yeah, this should be a performance of agent Smith. Yeah, kind of. I hope that this configuration are proper. Let's just double check them. Yeah, agent Smith application. Yeah, 2 period of processing time 2 second, concurrency level 2 messages, like 2 workers. Yeah, the configurations are proper. However, if we go back to agent Smith, this is agent Smith configurations, we will see that the capacity is this one, which means that agent Smith will be consuming messages pretty slow with agent Smith, like Big Brother will be consuming messages from his queue pretty slow with agent Smith rate limit, which means that Pitchkin, which knows only about Big Brother configurations, and we see the Big Brother configurations, basically 8 messages per like half a second, basically, which means that Pagecane will be delivering more messages than big browser is consuming from his queue, which means that at some point in time, as we just seen, the big browser will crash with out of memory, because there is no enough capacity in his queue, and it's gonna fail. That's why we've seen this failure. And what this say to us, basically, in order to properly configure rate limit, we always need to understand the full chain of services which are involved in our message delivery. Which means that if you have mobile application which is going to gateway, this mobile application has to know, let's say, like I'm in theory, hypothetically, has to know what is the capacity and performance of this service which is like recipient of this message. Of course, we have load balancing and more configurations, but it may happen that some service at some point in time will get this number of messages and will fail because we don't have proper control for this. So let's back to slides and let's do a short. First of all, let me confirm that if we configure the whole system working accordingly to Agent Smith kind of performance, it will work. Let me just do that. Let me stop Big Bro and let me start it again with Agent Smith config, and let me terminate Pagecane, and let me start instead of Big Browser rate limiting, which I have it here. Let me start it with Agent Smith rate limit. So all of the chain will have the same rate limit configurations, so in theory nothing should fail in that scenario. So we are starting. While it started, we are checking that Pagecane Agent Smith configurations are identical to Agent Smith configuration in Big Browser, which means that now the whole system has the same rate limit configurations, which are equal to Agent Smith performance. And now we see that our system works. There is no message dropped. There is no retries which are wasting our CPU. And that's basically something that we wanted to achieve. So it sounds that we are good and rate limit works. Let's say it works. We will see. Okay, so let's go back to our slides and let's do a short sum up of what we see. First of all, we applied a couple of strategies in order to solve a problem of message delivery, like resilient message delivery within our system. The first strategy is drop-in messages, which can be acceptable, but in the most scenarios, it's not acceptable. We tried the retry. So, yeah, basically Postilion Pagecane saying, hello, 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 and of course nobody is responding back because the department of Big Browser is busy. And finally, after some retries, Pagecane will fail because of timeout, because he got crazy. And we will go back to the same case when we drop in messages, and we've seen this scenario, this situation. And finally, in order to apply real flow control, we applied rate limit, which basically says that we don't have to send more messages per second than this. However, this was a little bit challenging because we had to understand the whole pipeline, how every service is configured, which is tough. So we kind of solved the situation, the problem, but is it a real solution? Because right now in our pipeline we have single Pagecane, single Big Bro, and single Agent Smith. But in reality, our gateway, which is represented by Big Browser, will be handling much more messages from different departments, like Postman departments, because there is a lot of senders. There is no single bottleneck represented as Pagecane, and there are a lot of kind of postmans in the world, and all of them have to send messages to security department in order to make sure that there is no suspicious things in this message, because this is the main idea of security department. So what's gonna happen if we run more than a single Pagecane in our case, using, for example, rate limit, since we understood that rate limit works pretty well? So let's do that. Let's try to see what's going to happen in that case. Okay, this is, we span an hour. We are moving good. And let me terminate Pitchkin for a second. Yeah, I'm stopping Pitchkin. Pitchkin is down right now. And now I will try to run more than a single Pitchkin. So I have in my config, I have an option, specific config, which says, okay, I want to run more than a single instance. I have like this property in the terminal, which says, okay, I want to run, for example, 2 or 3 instances in a row. And of course, we will see a lot of messages because right now I enabled the verbose mode, but probably we don't want to see all the messages. Yeah, we can try to see that at least 3 log of Spring Boot have started, but yeah, there is no reason to see all these logs. So for now, let's start. We see that the number of instances is 3. All of them are running with the same configurations. We see 3 log of Spring. And now at the dashboard, we should see 3 different instances of Pitchkin sending messages to Big Brother and then to Agent Smith. And here we go. Everything has crashed. What happened? You would say, wait, we just configured rate limit configurations, but it didn't work. It doesn't. What's wrong with that? Well, we have to think. We have to think, and we have to understand that rate limit is local rate limit. So every Pitchkin instance, every department knows that basically Agent Smith accepts messages and consumes them with that speed. But since they are not synchronized at this moment, they are not calling to each other and saying, well, is it my turn to go to Agent Smith right now or to Big Brother? No, it's yours. Okay, I will be going. There is no coordination right now, and that's the reality of most of the services. There is no coordination between them because this is waste of resources. They're not talking to each other, and that's why they are failing, because they know the same parameters and they try to go, and then they see, okay, Postilion Pitchkin 1 is waiting at the door, then the Postilion Pitchkin 2 is waiting at the door, and then the Postilion Pitchkin just stayed here and then say, hey, how long you are waiting here? So there is a queue, and the service of course fails because all of those services will be waiting too long, which is unacceptable. So what shall we do? The answer? Maybe we have to synchronize them. So what we probably need to do, we need to run some synchronization, and in real microservices, such synchronization can be, for example, an in-memory database or in-memory service, which is going to be issuing allowance and saying that, okay, right now we have this limit of rate, so you can go, you cannot go, you have to wait. And for example, in our application, so let me quickly go back to my common configurations. I'm using a specific library, call it Bucket4G. So this is the library that I'm using for this distributed synchronization. And this library is basically capable to talk and store data in Hazelcast, which is pretty fast in memory store. And then all the services can see what is how many kind of leases or allowance was used, and they would know whether they are allowed to go or not allowed to go at this moment. So this is basically the tool that we will be using. Just for your information, previously we used just Resilience4G, which has integration with Reactor. This can be useful if you decide to use like rate limiting within your single client. But if we want to synchronize multiple clients, Bucket4G can be a good solution. We will see if it's a good solution. And now we have a specific profile which says, okay, the page can run in distributed mode. It specifically enable rate limit distributed, which in turn run and enable, let me show it to you, base configuration. So we have Hazelcast instance here. which we create, which we create here, and then we configure our rate limit worker according to like presence or absence of hazel cost. So if hazel cost is present, we use hazel cost and we configure bucket for G. Otherwise, if we have different profile, we just use rate limit, or if nothing is kind of configured, we just use simple worker, which just send messages. Basically, no rate limit is enabled at all. So we have this configuration. So let's move back to our Pitchkin. Let's terminate them all. Okay, yeah, we killed all of them. We see that they're down. We stop brother, and yeah, Agent Smith is still working because he has like error strategy, so he will never fail. He will be just bouncing messages back with an error. And now we restart Big Bro, and now we use a distributed config. For Pitchkin. Send. Okay, it's not send. It's just distributed. Distributed. Let me check. Is it distributed? It is. And we start Pitchkin. Okay, this is single instance. We wanted to start multiple of them. Yeah, okay, let's try just with single instance to see that bucket for G works. You just start it, and yeah, it works. Nice. So a single instance still working, which is kind of a confirmation that awesome, all good. But now let's try to run the previous scenario where we got multiple instances of our Pitchkin service. So we have like this instance number configuration, and we say, okay, we want 3 Pitchkin to be ran, and we start. So we have instance number 3. We have send rate limit configuration according to Agent Smith configuration. We have distributed scenario, and we see that 3 services have been run, and they should appear there in a second in our dashboard, where we can confirm that this technique works or not. So let's see. It takes time, of course, to start, because right now we have hazel cost. And yeah, we see that they're running. We see that the Pitchkin 2 took his leadership first, because he was the first who has started, and he started messaging with initial speed since he didn't have any limitation. But we see that the system starts balancing, and we got kind of equivalent number of messages, and everything is working, which is okay, which is good, which is basically saying that and confirming that our system can be stabilized and can work in resilient fashion if we have a single hazel cost instance to which we're gonna go and to which we will be talking in order to synchronize states between all the services, between all the clients, which can be acceptable, of course. So this is a solution that you can use. But we are in microservices world. And as I said at the very beginning of this talk, in microservices world, we have uncertainty, which means that we have latency. This latency is not always stable, which means that if something goes wrong, if we got a little bit more time to process resource, what's going to happen? Will it work or will it not? So let's see. Right now we want to emulate the full real world scenario with all the delays, with all the real latency, to make sure that hazel cost used for rate limiting works as expected. We want to confirm that. So I'm stopping my Pitchkin service, I'm stopping my Agent Smith service, and I'm stopping, of course, my Big Bro service. And now I'm running my Agent Smith. It's enough to run Agent Smith with random delay. So I have this extra profile, call it for Big Bro. I have it application random delay. And here I have random delay, which can be within a second. So it means that it's random. So it can be 0, it can be 10 extra miles, it can be 100 extra miles, or it can be just 1 extra second to process this response. Because you know that if too many pitchkins are coming into the room and saying, hey, what's going on, the attention of the worker go from the main job, and you as a developer know how it's important to take attention on what you do. Because if you lost it and you forget what you've been doing just a second ago. That's why if we emulate real microservices, we have to take into account this possibility of delays as well, of network and all other things that may happen. So we run our agents meet with this random delay config. Yep, it's random delay. Yeah, it's random delay, all good. And of course we start big bro with the same config. We just need to introduce at least at one service this uncertainty. And then we run our pitchkins with the same setup. And we will see what's going to happen. Will it work or will it no? In the meanwhile, I'm ready to answer for some questions, like while it's running. So if we have some, please take them on. Am I online still? Okay, I'm online still. All good. And it's running. Okay, we see that it's running. We get some messages. We get some speed. But let's see if it worked as expected, because something suspicious is happening here. Our buffer is overwhelming. But according to our config, this producer, this big bro, doesn't have to send more messages than 2 or 1 per second or 2 per 2 seconds. But we see that the buffer is overwhelming, which is not good, which means that big bro is sending more messages that the agent meet is capable to handle. And we see that big bro just failed. It doesn't work again. What's wrong with that? And the answer? Yep.
Okay, yeah, I'm finally online. Sorry for the delay. And we have a couple of questions in our chats. So first of all, Bella Boros is asking us, when do you suggest using RSocket instead of Kafka, or vice versa?
So yeah, we will get into that. Basically, Kafka is a queue. So it's the same queue as we see right now, but it's just distributed queue, which means that it can scale, it's more reliable. But the point here is that there is no unlimited resources. That every service, every computer has its limit. And if for some reason, if at some point in time your application will send more messages to Kafka than it can store on disk or handle in memory, then your Kafka instance gonna fail. And the same can happen to any distributed system. If for some uncertainty, if for some fire of messages you wasn't able to balance it properly, to store it properly, then you fail. And that's it. I remember scenarios where it's similar situations, like half of the Hazelcast cluster were failing. Basically, it was failing, and most of we got like in production this brain split problem, because half of the services were thinking about this one, another half was just failed and restoring, but since they wasn't able to kind of desynchronize in time, messages was just lost and dropped, and that was just mess. I remember how long we solved this mess. So and the problem with that is that kind of every service, every system can fail. Of course, Kafka is pretty reliable and kind of really resilient system, but now you have to think how many how many resources you would spend and how much money you would spend on maintaining such a cluster, how many nodes would be required for a cluster, for Kafka cluster, how many kind of memory and disk availability should be allocated for those services. These all questions are related to money. And with RSocket, where you have, I will be talking about RSocket in a second, with RSocket where you have backpressure, where you have advanced resilience, you don't have to queue and store anything. You just send whenever you know that the recipient is ready. And that's what we want to have. And that's why all this rate limiter and other technology are failing. They're good. I'm saying they're good. They're awesome. But they're failing, and we can do better. And that's why we are moving to our slides to do a summary. First of all, we've just seen that Hazelcast, the distribution synchronization, has failed. But in order to make, if you don't want to use RSocket and you still wanna kind of control your capacity and stability of the system using all good technologies, then instead of rate limiting, you have to use concurrency limiting. I'm suggesting to look at this great talk, which is explaining from John Moore, who is explaining why concurrency limiting is better than rate limiting. Because actually concurrency limiting preventing and handling this unexpected timeouts, and instead of sending number of messages per period of time, it just sees that the concurrency is not going over, which is what we basically need. So we still have remaining problems. What we've seen is just a mess of complexity. We have redundant layers of complexity. In one scenarios, we have to use different libraries. All these libraries are not always identical in different languages. If we use synchronization of single, like between multiple clients, we need to understand like what library we need to use, what store and memory store we need to use, and how much memory and so forth and so on, which is a lot of problems. And all the parties, your client, your server, every piece of your system has to understand capacity of another, which is hard to implement. And that's why we've seen a lot of talks related to chaos kind of this chaos management, chaos engineering, where people develop complex algorithm to kind of to predict the capacity of the server at this moment, trials, samples, and so forth and so on. So this is hard. This is just hard, because client is guessing what's going on in the server, and I guess this is the main problem. So if you may argue to me, okay, what you've shown was just technologies back in 2010, but now we have much more advanced technologies like service meshes. But the point here that service meshes is just a nice marketing solution or proposal, because under the hood service mesh just uses the same technologies from 2010, and we've just seen that they're good, but not always. And sometimes your system may fail, and if you fail, it will cost you a lot of money if you are Netflix or Amazon, for example. And you say, okay, today we have more advanced technologies like Docker, Envoy, Kubernetes, and the other set of great technologies. But again, they use the same things, and they just hide this complexity for our eyes, but this complexity remains unhandled under the hood. And all this service meshes still uses this Redis and Hazelcast, and who knows when they go on fire and what's going to happen when they go on fire. And I can recommend a couple of readings related to Redis went on fire and how the whole system just crashed because of one node of Redis failed. So we have a huge problem. All this stuff is a little bit outdated, and we know that we can do better. And the problem with this technology, this is my own opinion. I'm not kind of saying that RSocket is a silver bullet. No, it has its own limitation. But I'm saying that the problem that all this technology are solving are symptoms of another problem. And the problem that they try to solve is that like the protocols that are used underneath are not like bidirectional, not peer-to-peer. There is no communication between sender and recipient. And if we have this communication, so the sender know in advance that recipient is busy or not, because recipient just told to this client that no, I don't have capacity, don't send me messages, then we will solve all the problems. And RSocket basically helps with that. So yeah, let's make 1 or 2 minutes question session if we have any other question, because I just answered one question, and we can quickly move to RSocket, and I will show how RSocket is awesome.
I believe we're almost out of time, so let's proceed without any additional questions, and next we will discuss them in our discussion zone. Guys, are you okay with it?
Yeah, I need just 15 minutes to show the awesomeness of RSocket. Before I need to prove that we need to solve problems, and now I can just prove that RSocket solve them. So RSocket...
We may give you just a second. So yeah, we may give you 7 or 10 minutes.
Yeah, it's enough. So I'll speed up. So RSocket is awesome protocol. It's application level protocol. It brings peer-to-peer. It brings streaming. It's bring normal daily type of messaging that you get used to for many years, like request response. It has reactive streams backpressure. This is basically the mechanisms that I just explained. When a recipient can say to a publisher that he is ready to receive messages, where we have this kind of pushback from the recipient to a publisher that we are not ready, or we are ready to consume messages. And this mechanism was proven by time, was proven by many reactive libraries which we are using, including Project Reactor, including RxJava, including Eka Streams, and many others, that this mechanism is good. And in RSocket we have even more advanced mechanism called leasing. So this is advanced resilience, when if for flow control for reactive streams backpressure, you have backpressure within your logical stream. For leasing, you have backpressure for the whole connection, for the whole number of requests that your requester can issue. So basically this is concurrency limit or rate limit driven by server. So client has nothing to do, has nothing to guess. He just received some information from a server about how many requests it can do. And we have other awesome features like resumability, fragmentation, and you can extend protocol if you need that. So all of this support. And on top of that, we have a lot of good stuff. So it's binary protocol. It's flexible in terms of communication, and it's of course supported by many languages. And we are expanding our community. And even today we have Swift support, Kotlin full native support, and more is coming, which is great. And the coolest feature that I really like and appreciate in RSocket is flexibility, which brings flexibility in terms of usage. If you need WebSocket, you don't have to rebuild your app. You just use WebSocket or TCP. Or if you need performance, there is HTTP3 or Aaron. And you don't need to stick to some protocol and then rebuild everything. You can use in part of your system one protocol, like one transport, in another transport, and that's how flexible will help you build your good microservice application. But first solution that we can apply is basically with reactive streams, and this solution you can see how it was done a couple of years ago when I've been talking with Eugene Borisov at GEConf, and you can basically look at this presentation and get an idea how it can be done with reactive streams, only with reactive streams. The problem basically, there is no problem. RSocket solved all the problems, and we got like stable performance, but in the cost of changing our API. What I mean is basically we started using Flux and publishers on the whole pipeline, and we lost this kind of request response behaviors. And we want to kind of preserve this request response behaviors, because in many systems we are not allowed to just migrate to a single stream. And in many scenarios, reactive stream, just a single stream, is not applicable because we have multiple services sending messages to recipients. So streaming is good, but it's not always applicable. That's why we want to preserve our behavior request response that we had this HTTP and using RSocket. And we want to see if RSocket helps in solving and kind of preserving stability. So instead of flow control, we want to use rate limit or leasing. And let me quickly explain how leasing works for inside RSocket for you. So we have Big Brother and we have Pechkin. So at the very beginning of communication, Pechkin does nothing because he is not allowed. Because if leasing enabled, requester is not allowed to send a message unless, yeah, basically this is a situation, but Pechkin is not allowed to send any messages unless a server sent an allowance, an information that a particular client or requester can do request. So once such a request or lease is kind of received, Pechkin is allowed to do 10 requests, and a part of that, he has like a time limitation or time box during which he can do this 10 requests, because server reserved this capacity for this particular requester or client. And that's why during this period of time and using this number of requests, Pechkin can send request and receive response with no problem, because he know in advance that this is the allowed capacity. Once time or issued number of requests went out, Pechkin is not allowed to do anything again, and he is required to wait until the next lease or the next allowance is received. So basically, as you may notice, this mechanism looks pretty similar to rate limit or concurrency limit, but now it's absolutely driven by a server who knows his capacity, who knows what number of messages are in progress right now, what number of memory are used, and so forth and so on. And based on this info, the server can guess whether a requester is allowed to send request or not. And that's how the problem can be solved. And I really like it because it works. So let's have a look. Let's quickly move to our socket scenario. First of all, let me quickly switch to our socket. Check out revision. To our socket branch, and let me show you what's going on under the knees, under the hood in our socket case. First of all, we brought our socket dependency into our project. Here we have our socket bomb, the latest, the greatest bomb that we're gonna release next week. And we have as one extra dependency here, not here, there, not there, okay, maybe in the main. We have, Spring Boot Starter, our socket. Yeah, we have our socket right now. And let's quickly have a look at our changes. Basically, let's have a look at controller, and yay, nothing has changed. We still have controller annotation, we still have message mapping, similar to what was in WebFlux, which means that technically nothing has changed. What we have on the sender side, well, not much of the changes. If you remember what was there before, here we had web client, now we have our socket requester, which is a similar mechanism to web client, and it uses the same technique, the same setup. And now we say, okay, we want to route message to this endpoint, we provide a message, we call send, and we transform the response as it was before. So from the implementation perspective, if we migrate from WebFlux to our socket, not much to do. Great. And this code is available on GitHub, so you will be able to confirm that I'm saying true, that I'm not lying to you, and it's really smooth migration from WebFlux to our socket. And yeah, that's basically it. The other services are the same. So The only thing that I want to show you is setup of RSocket requester, and I want to show you how it's easy to configure this leasing, this native protocol-based kind of concurrency limiting mechanism in RSocket. So this is how we configure RSocket requester. On the client side or connector side, we just say, okay, we want to enable lease, and once lease is enabled, the requester will follow the allowance provided by server. So, okay, good. On the server side, since we run both the connector and the server, we say, okay, we want to configure a mechanism. So this is a mechanism that we want to use. And at this moment, we use well-known library from Netflix, really good library from Netflix, which is called Netflix Concurrence Limit. So this library is basically used to calculate the capacity, the number of concurrent requests from at this moment. And since server knows everything what's going on, and the server he knows how to properly calculate concurrency and capacity, because it's much easier than predicting it on the remote side. And once we know, we will send leases over the network. And if you're interested, we can discuss it in the backstage after this talk, how this mechanism properly works on the protocol level. But this is how it's configured, and all this setup is using concurrency level queue capacity of this service. So service know what is capacity, and it configures concurrency limit according to its capacity, so the others doesn't have to guess what's going on this server, which is awesome. There is this isolation. There is no leak of information behind the servers, which is awesome. And now we want to run. So first of all, let me stop all the services. Oops. I switched the window. And let me go back to a different tier, go back to RSocket Advanced, RSocket Advanced, where I already prepared all this code base that you just seen, RSocket Advanced. And now I'm running, let me stop to make sure that it's stopped. And now let me run everything. And now I'm keeping the same configuration, the same random delay as it was before. And instead of error strategy, I will be using terminate strategy to say, okay, we are risky. We want to make sure that our socket is really solving the problem. And if we got out of memory exception, we will kill the service. So we want to make sure that our socket won't cause out of memory and will preserve our system stable. So I'm running Agent Smith. I'm running it's the same terminate, and instead of rate limit, I'm not using rate limit anymore. I'm using send fail. So I'm only relying on our socket strategy and nothing else. I'm saying if I send too much or if I receive an error, I should fail. And I'm running Pitchkin with the same, no distributed, nothing distributed anymore. Only send fail as it was before. And we run, let's start from one instance to see that it works. And then we can increase the number of instances to make sure that our socket works even at scale. So it's running. And our system is working. Nothing is failing.
That's wonderful.
Yeah, just 1 second. Give me just one final second. Sure. to say, okay, so it's working. Lease is issued properly, and if we're gonna look inside the internals, we will see that everything is fine, nothing is broken. We see that the system is stable, and at this next step, we have we have even more advanced configuration. If we have more time, I would show you how we can use even load balancing So let me just check out.
Oleh,
Just
so sorry for interrupting you, but we really out of time.
1 second. I'm showing how easy we can configure load balancing, and we can stop. So I'm switched to load balancer, to real distributed scenario where I'm using Spring Cloud Discovery for kind of observing other clients. And in our socket, we have built-in load balancing, which you can use. And we have like load balancer, we have everything that you need. And you can connect to multiple clients and balance your load based on this provided issues, which is great. And it works. You can try it. I recommend you to check out the repository that I will share after this talk, and you will see how it's easy to use RSocket and solve all these microservices problems. Just final word. I'm saying that everything is good. We have RSocket. I recommend you to look at Steve Guri talks about predictive load balancing, which is implemented inside one of our load balancing mechanism, and this technique basically is used on top of leasing. So everything is predict. But this is not the end of the story. We have broker. This is the future, and this broker you can solve even more. So with that last word, thank you for your attention. RSocket is awesome. RSocket solves a lot of problems. I recommend you to try it yourself and share with us your feedback and your experience, because we are improving ourselves. We want to bring more attention to the protocol, and your help and your feedback will help us, and we will improve the world of microservices. With that, thank you. And if you have more questions, let's chat at the backstage.
Okay, yeah. Thank you very much for this wonderful presentation. Just next time when you will ask for 1 hour and a half, I will increase it for at least 1 hour.
2, 3 is perfect. 3 hours is
yesterday
perfect.
we have 5.5 hours of Zhenya Borisov presentation, so I think you may beat this record. Okay, saying this, Oleh, again, thank you very much for this wonderful presentation. Discussion room is open. Now we will have link for the discussion room in Telegram chat and in YouTube chat. So guys, if you want to chat with Oleh more about RSocket, please follow this link and go to discussion room. Yeah, it already appeared there. So Oleh, thank you again very much, and Sasha, thank you very much for moderation, and thanks for being on Java the Day.
Thank you, folks. It was pleasure being there.
Thanks a lot.